So today we are excited to welcome Professor Jakob Runge, who heads the Climate Informatics Working Group at the German Aerospace Center's Institute of Data Science in Jena since 2017. He's also a guest professor of computer science at TU Berlin since 2021. His group combines innovative data science methods from different fields like graphical models, causal inference, nonlinear dynamics, deep learning, and closely works with experts in the climate sciences and beyond. So Professor Runge studied physics at Humboldt University in Berlin and obtained his PhD at the Potsdam Institute for Climate Impact Research in 2014. He was funded by the German National Science Foundation, and his thesis was awarded the Karl Ramsauer Prize by the Berlin Physical Society. In 2014, he won a 200,000 fellowship award to study complex system from the James S. McDonnell Foundation and joined the Granheim Institute Imperial College from 2016 to 2017. Finally, last year, he won a starting grant from the European Research Council for his interdisciplinary project Causal Earth, which also, as part of the project, provides regular updates of the software Typramite, which is available on GitHub and is very easy to use for climate scientists. I would highly recommend it. It's an open access time series analysis Python module for causal inference specifically. And today he will give us an overview of his recent efforts on causal inference in Earth system sciences. And with that, thank you so much for accepting our invitation, Professor Runge. And I'll let you take the floor.
Thank you very much for this kind introduction and the opportunity to present here. It's always nice at least to come virtually there. I've been many times there at different places, and yeah, it's always great to be in the US science community. So today I will talk about the title as stated and give you more of a introduction rather than talking about my work so much, because I think it's good to learn about the concepts here. And I hope to stay within 30 minutes and well, otherwise give me a card. So there was in this white screen now a little video that my PDF viewer in this presentation mode wouldn't show, which just shows the dynamics of precipitation from like NASA satellite recordings. And to this, I'm telling you, like, the Earth system is a complex system, and we have a lot of data, which is quite unique compared to other fields maybe. And in addition to data, we have a lot of physical knowledge about the Earth system. And what my background is from physics and causal inference is about what can we learn about causal relations from the data alone without intervening in a system, which is not possible in climate. So that being said, there is some, some backlash on causal inference in the past, based on someone very famous that most of you will know by a famous correlation coefficient. So Carl Pearson was a pretty preeminent opposer of, as he says in his very elaborate British accent, and I'm not trying to mimic that, beyond such discarded fundamentals as matter and force lies still yet another fetish amidst the inscrutable arcana of modern science, namely the category of cause and effect. So I kind of took an account from Judah Pearl, who I will mention on the next slide, who phrases this as one of the big obstacles in bringing forward a notion of causal effects and causal inference based on purely data analysis. And this was one of the main obstacles in Judah Pearl's view. So Pearson famously framed this mantra, correlation is not causation, and instead what you got is correlation coefficients. So let's see what can we do beyond. So what these people down here, Judah Pearl, Peter Spirtus, Clark Leamer, and Richard Shines, and many others, of course, but they started this in the 80s and 90s, is the science and the art and science, as if you call Pearl, of cause and effect. So not generally can you read out causation from data relationships, but causal inference, the field that I'm in, is really about identifying assumptions, which is the crucial word here, and methods that enable to learn causal relations from observational data. So I will try to give you an intuition how this is possible. So we will talk about observational causal inference and then causal discovery, which somewhat is a subtopic of causal inference, and then some application examples that are maybe more in the Q&A. Let's see. So what is causal inference about? Quite shortly, it's a mathematical language for causal notions such as cause and effect, and it provides methods and assumptions for answering questions from data. And lastly, this point on causal discovery is also about learning causal graphs from data if you don't want to make any assumptions about the underlying relationships. So I will get to that in this talk. So one could say the fundamental question of causal inference is that consider that you have two events, or let's rather consider variables x and y, and these variables x and y are whatever quantity you want to look at in your research. And the question is then, how can we determine whether and how x causes y? So if you were an experimenter, and the classical approach to science, of course, is to experimentally manipulate x and keeping all other conditions exactly the same. So that's an important, of course, experimental setup to only vary the quantity that you're interested in and otherwise control the setting. And if this results in a change of y, then you would say x causes y. So that's kind of what we were doing over many hundreds of years, of course, as put forward by Galileo Galilei. And such an idealization of an experimental manipulation is now in causal inference terms to as an intervention in X, and I will formalize it a little bit. So quite simply, the kind of toy model always used in such talks would be that if you look at data on a lawn being wet and a sprinkler turned on, then you would see both of them being highly correlated. And if you look at their scatter plot or so, you would see them both being related. But how can you read off causal relations from that? You know that turning the sprinkler on makes the lawn wet, but on the other hand, making the lawn wet does not turn the sprinkler on. So the critical notion is here this idea of keeping all other conditions exactly the same, which is what we will try to bring over to the observational space. So in general, when trying to do, of course, experiments in a climate context, the challenge is that usually it would not be possible to experiment in real climate. It's, of course, either just infeasible or just ethically questionable. Well, maybe you're a proponent of geoengineering, of course, that is such a experiment, and we better know what we are doing there. So in general, it's not possible to intervene in variables, say here, environmental factors causing aerosol concentrations in the atmosphere, and these in turn affecting clouds. And our goal would be maybe to investigate, well, how much are aerosols affecting clouds? And if you want to determine that effect, you would have to control for these environmental factors, or you intervene in aerosols and look at the effects on clouds, which is not in general possible. So the other challenge that I would put forward is that I said before, we have quite, compared to other disciplines, a lot of knowledge from the basic physics of Navier-Stokes, energy equations, and so on about the climate system, which enabled us to build simulation models. But often still, we are in the situation that we want to learn about relations among more macroscopic variables, for example. So I've collaborated a lot with people working on teleconnections, for example, and questions arise like, what's the relation between Arctic sea ice extent in winter, mid-latitude weather in summer, or ENSO as a main example of which other regions are affected by ENSO. So I mentioned we have a pretty awesome tool, which is global climate models. And these are primarily examples of doing interventions in the physical realism of a model. So that's the limitation, of course. We have several models. We have different models that will not model all parts of the real Earth. And this limits the interpretability of any experiment that we do with these. But nevertheless, we have a tool there that can help us, and that I, in my more future research, try to combine with the observational tools that we have. And one of the application examples, is something in that direction. The other option is what causal inference is about, is to use the data that we have, which in our case is also quite ample, at least for the past 30, 40 years, the satellite era, and use this data from the real world to see what we can learn about causal relations. And yeah, this seminal work I mentioned already is done by these authors, not in climate, of course, but in general, the theoretical work. So in the next few minutes, I will go about defining what we mean by causal inference by going into the notion of a structural causal model, an intervention, what that is mathematically, and define what is called identifiability, namely when you can actually, the assumptions under which you can actually learn causal effects from data. So a structural causal model is kind of it's not a statistical model, but it's the mathematical object that we use to define what we mean by interventions. And if you go back to this small example of aerosols, clouds, and other factors, you would write down a model like this, which is for physicists quite intuitive, of course. Aerosols are a function of the environmental factors, and then this eta is unobserved variables. So that might be stochastic fluctuations modeled in some way. Or in general, what these structural models assume is that these factors that we put in the eta are basically ones that we do not resolve, but that we assume to not affect the other variables like clouds and environmental factors. So such a model specifies the direct causes, the parents of each variable, because that has an incoming error. And the functions are, in this language, independent mechanisms by which nature determines the value of each variable based on the values of its direct causes, plus the random fluctuations. So the difference to a statistical model is that we have this colon in front of the equality sign, which is really means an assignment. You cannot just solve the function, the first line here, for environmental factors or so. This is not a statistical model where you can, or a mathematical equation, but it's an assignment mechanism. And that is how it needs to be interpreted. So what is an intervention in such a model? That would be modeling this experimentally manipulate X by keeping all other conditions the same. Well, here it's basically just done by in the framework of do calculus. So this is the mathematical framework of how to define interventions. And this is the distinction to statistical notions. So here, what do X aerosols and assign it a certain aerosol concentration means is you go from the previous equation, the prior to the intervention, and now you assign X to some value. And what this does in this structural causal model and the associated graph is you delete the incoming arrows, which is the same as you in the setting intuitively. And then based on that, you can make inferences about how here, for example, clouds are affected by this intervention in aerosols. So how does this change now the distribution of clouds? So the general formalism is really giving that we have this mathematical, solid mathematical formulation. We can then try to find assumptions under which the quantity of interest, namely the probability of y given do x, really the intervention, which is hypothetically then, of course, under which assumptions we can relate that to what we can observe from the data. Because in general, this will not be the same as the probability distribution of y just given x. So this do is the crucial difference here. So a big part of the theory of Pearl is really about deciding or giving you criteria to decide whether a causal effect of x and y can be identified from observational data, and how that can be done, how it can be estimated then. So I will not be much formal here, but rather convey the idea through examples, because I think many of them are intuitive for you and you do that already. And it's just something where you can build upon and maybe go to more complex cases. So say you have three variables x, y, z, and you are in all these slides now interested in the causal effect of x on y. And I put some coefficients here to just say what if that relationship is actually linear. And you're now interested in the effect of x on y. And what you now put in as your expert knowledge is that I know the graph, the relations, but I do not know the coefficient c. I do not know how strong this effect is. But I have my expert knowledge on the causal graph, which is quantitative knowledge. And Pearl's theory would now tell you, which you would intuitively do anyways, you just regress y on x here if you assume it's linear, or you fit a complex model like a deep learning model or so of y on x to estimate the effect of x on y. And this is fine if this is the graph that is underlying. If, on the other hand, do you have a confounder, there's a variable z that causes x and that causes y, then you cannot just fit a model of y on x. What you would get, in essence, is actually not just the effect c, not just the coefficient c, but you would get also a contribution from z. So it would be something like c plus a times b times the variance of z here. What you get as in a linear regression framework, or also the correlation would be confounded and therefore inflated here. For example, also if c is 0, if there's no effect, and you look at the correlation between x and y, then you would get a non-zero correlation, even though there is no link, there's no causal effect. So how do you overcome this? Well, what you've done already in your analysis, I would say, is you control for the confounder. And that then is basically just fitting a model of y, not just on x, but on x and z, and then looking at the coefficient that corresponds to x in a linear framework or in a nonlinear framework. Given that fitted function, you can then use that fitted function to estimate causal effects by looking at particular values of x that you then put into this fitted function f, given, for example, a more complex machine learning model. On the other hand, if your causal graph looks like this, and I always mean we are now always in a setting where you have expert knowledge, but you just don't know the quantitative relations, then if that is the graph, the approach would be to not condition on z, because that would actually block the relationship. And also, if there's a link between x and y, and you condition on this z, what you then actually get is the direct effect, where you block the indirect effect. Coming back to a confounding example, if the confounder is not observed, so you cannot do anything like condition on it, then Pearl's theory would tell you in this case, well, you cannot identify the causal effect, so there's nothing you can do. So you either try to get the data of L or come up with some more involved approaches that will come later on, which sometimes work. Another pitfall is the common effect. So if x and y both cause a variable here, s, and you maybe have the idea, well, let's just throw everything into my regression function. So I'm kind of safe because I try to control for everything, so that's fine. But that's a very bad idea, and that is what also these Pearl theory tells you. It's especially bad to just condition on an effect of the variable y here, because that leads to a bias. You would actually not estimate the effect of x on y, but again get some contribution due to that common effect. Not sure that is intuitive to you. It wasn't to me, but now it's kind of in my mindset that this is a bad idea. And while you might be aware of this when you do it explicitly, another way to frame this problem is when you have data that is not sampling the population, but the statistical population, sampling your process like randomly, but only a subpart of it. And maybe that part is determined by the variables x and y. Like an example is that I had in this aerosol clouds. You cannot measure aerosols when there are clouds. So it's actually a pretty bad example if you look at this from a observational data perspective. And then your sample is conditioned. So your sample is only there, the non-missing values are only there for a subsample. This also constitutes something in this direction. Here's a more complicated case, which is where this theory really becomes useful, I would say. And for such cases, we have criteria for identifiability, and one of them being the backdoor criterion that I will just state because it's maybe good to see what actually the theory does rather than just showing examples. And this criterion tells you that a set of variables Z, which is a subset of your observed variables, satisfies the backdoor criterion for identifying the causal effect of X and Y. So it gives you the correct set of control variables if Z blocks all non-causal pairs between X and Y. So for example, Z3 here, if you condition on that, then, not sure you can see my mouse, but a non-causal path here from X to Y would be going through L2, Z2, Z3, and then Y, or through Z1, L1, Z3, and then Y. So it's called a backdoor path sometimes, which is why it's called the backdoor criterion. But if you control for Z3 here, you block that, and that helps you to get the causal effect of X on Y, which is just this link. Another optional adjustment set, that's another name for this, is to use Z1 and Z2. They also, these two together block all non-causal paths. So that's the rule of how to block paths, and the rule of not conditioning on descendants is the other part of this criterion, which says that no element in Z is a descendant of Y or mediators. And mediators would be an intermediate variable M here, so you shouldn't include such a variable in your regression model or such a variable here. So those are the two simple rules, and that tell you whether a certain set of control variables is suitable. And the fact that there are more than one is interesting from a theoretical perspective. And I, for example, have recent work telling you which set to use to get an optimal estimator in terms of lowest error. So why this is useful? Well, there's a theorem telling you if you have a set of variables Z that satisfies this criterion, then your causal effect, the left-hand side here, P of Y do X, is the same as the sum over Z, the variables, the values that your control variables take of P of Y of X given Z times P of Z. So this looks more complicated than it is. This is just in regression terms, you just put all of these Z in your regression model in addition to X, and then look at the coefficient of X. This is the same as this if you assume linearity, but this is a more general formula. So this is the backdoor criterion, which works whenever you can find a set that suffices this requirement. If, on the other hand, you are in a confounded situation, then you can use other tools of Pearl's theory, for example, the Confounder criterion, which works in this setting here, if you have a mediator that is not affected by the latent variable. Okay, I think this was important because this is something that helps you in your everyday analysis. And now I come more briefly to another part, which is as follows. So the previous section really told you knowing the causal graph of the data generating process, which is an assumption that you make and that you have to justify in any analysis. Then you can determine with these tools here whether and how a causal effect can be identified from data and estimated. So how to get the causal graph if you have less knowledge. So one, of course, is to relate to other domain experts, general reasoning, the literature, hopefully not based on correlations. And the other option that causal inference, causal discovery is about is to learn it from observational data. So this learning the graph from data is based on a simple fact, namely that the structure of a causal graph often has observable implications in terms of conditional independencies. So this is just statistical relationships conditional on other variables in the data, in the observed data. And the intuition behind is really that such dependencies come from an underlying causal relationship, which is one of the assumptions here. And conditioning, I already had this backdoor criterion. This is conditioning, controlling for, conditioning, partialing out, all mean the same thing. And that can block and open the flow of information. So, simple example, if your underlying process is this causal chain, but you don't know this causal chain, you don't know it, you just have measured x1, x2, and x3, then if you look at their relationships, you would see that x1 and x3 are dependent, which is this, this non-orthogonal cancelled out orthogonality relation. X2 and x3 are dependent, x1 and x3 are dependent. But you would also measure that x1 and x3 are independent given x2. So the partial correlation of x1 and x3 is 0 given x2, if you remove the effect of x2. So this is the important thing here. What independencies do you get in the data? Now look at this example. It's not a chain, but it's a fork. If you look at the independencies that this implies, you get, unfortunately, the same one. And that means you cannot distinguish this motive from this motive. On the other hand, what you can distinguish is this motive, because here we actually measure that x1 and x3 are independent, while they're actually becoming dependent given the central node. So again, 3 nodes, but different conditional independencies. And so you can, from these independencies, conclude on this relation, on this collider motive. On the other hand, if variables are disconnected, you would measure independence also between the marginals here. So in more complex cases, you can iteratively test each pair of variables on others, and there's smart algorithms to do that, and they then result in graphs that you can get out of them. So you don't have to do that yourself. That's actually what I worked a lot in the past years, to come up with algorithms that are efficient in identifying causal graphs from data. So for example, here you would get this range of possible graphs if you just measure the left-hand side relationships. x1 and x3 are independent given x2. And these are observationally equivalent. So that's the limitation. You cannot go beyond that. But there's many things to circumvent that. And the other example here, you would be able to conclude that they have to be causes of x2. So again, to make these conclusions already, you cannot just use data and not assume anything. You have to make assumptions. And that's the strength of the theory, to tell you which assumptions you actually make. So here it would be the existence that there is an underlying structural causal model, and that fulfills the causal Markov condition, maybe more technical. Another one, more technical, is faithfulness. But in a sense, Markov and faithfulness just relate dependence in the graph to dependence in the data. And maybe you have to assume causal sufficiency, that there are no unobserved confounders. But the good thing is that you don't have to. That can be dropped, because it sounds unrealistic, and it is often unrealistic. So that can be relaxed. I'm speeding a little bit up, but this is maybe material that you can look at later and look at some papers for references. So there's different algorithms that I mentioned that help you to unravel these graphs from the data. And they work under different assumptions. And this is called the constraint-based causal discovery framework. Then there's another framework that is also point of recent research, and that is this structural causal model-based approach, where you make more assumptions than just Markov and faithfulness, but if you are able to make assumptions about, well, it's linear and the noise distribution is non-Gaussian or so, then that also helps you to identify relationships. So this is covered in another paper of mine. So causal relations in time series are actually easier to do in a way, because when you look at a time-resolved causal relations, then, for example, x2 causes x1 at a lag time of t-1, which might be 1 month or so. Assuming stationarity, you would then maybe assume that this holds for all pairs. And in that way, the graph looks similar, but they are now in a time-resolved fashion. And time helps you because you can have lagged effects. And for these, you always know that they can only go forward in time. And therefore, everything that is lagged, you already know which direction it goes, and you don't have this problem that I had before in the chain where you didn't know whether it was a fork or a chain. So here, for lagged effects, that problem is overcome. Not so for contemporaneous effects. So these are the parents in this time result graph. If you look at a summary of this, then, for example, what you go down there is a feedback loop that often can be resolved as not a cyclic graph anymore in time. So you can see there's no cycles in the time series graph, but the summary graph has a cycle, which is something that theorists don't like. So summarizing, time resolved relationships make causation easier, but statistical issues arise, and this is what I've treated a lot in my work. So maybe stop at that and tell you that you can look at algorithms that I've developed in the past that go deeper into this problem, assuming causal sufficiency and without assuming causal sufficiency, so making less assumptions and therefore getting less informative graphs, just to warn you already that there's no free lunch here. Another concept, of course, that you can frame in the same way is Granger causality, which also requires causal sufficiency and also is limited to lagged relationships. So in this paper that came out 2 years ago already, that we come up with a way of giving a perspective on the different approaches that you have in the literature, and to kind of frame them in the different concepts, from Granger causality to state space models that some of you have maybe come across, and these network learning algorithms that I just described, and the structural causal models. So there's different ways that all try to address the same problem, and they all make different assumptions, which makes them powerful in one of the other settings. So the challenges of all these approaches are also summarized in this paper, and I will not go into detail here, but they range from having nonlinear dependencies, which requires you to adapt your fitting function or your conditional independence tests, to having, of course, the problem of unobserved variables, to having time subsampling satellite that do not sample every hour or so, but maybe traverse a certain region only every 11 days, while your causal processes happen faster. That's an issue, of course, but there's work on that. You may have missing values, you may have selection bias, I mentioned that, dating uncertainties in paleoclimate. And while many of these are unfortunately not yet addressed, but we're working on it. And this is also to raise awareness in the community about these issues and how they're being addressed. So with that, I'm kind of finished with the overview part, and can maybe take 5 more minutes on going through some examples that is more as an exposition, and we can then look into them if you're interested in more detail. So some references. So this is again more for later if you look into the slides. But one example that I find very nice by McGraw and Libby Barnes, and that they feature in their paper, is that of ENSO versus surface air temperatures in the United States. Well, not in the United States, all over America. And if you look at correlation, lag correlation between the two, then you see that ENSO leads surface air temperature in America. And the red thing is just, well, significant at some alpha value. But if you look at the other direction, so whether temperatures there also lead ENSO, then you get maybe basically a similar picture. So from correlation alone, you cannot really assess what causes what, which I hope is clear by now. And even a simple thing as bivariate Granger causality here helps you to get the correct answer in this example. So again, if you look at lagged Granger causality here, then you see that ENSO Granger causes these surface air temperatures, while in the other direction you get no significant relations mostly. And the ones that you get are basically false positives, arguably. So here it already helped to use Granger causality, which does not control for other variables, but just for the past. So the past of a variable is already a confounder. And that's important to know when you use correlation or univariate regressions. Okay, that is over now, that sentence. Another thing that I have here is reconstructing the Walker circulation. So here I use that as an example in this paper because it's kind of a ground truth example, one of the few ground truth examples that we may maybe have in this teleconnection research. And if you look at West, Central, and East Pacific data, and the little table here is actually just commemorating Sir Gilbert Walker, who was the first one to measure pressure relations at different stations and give rise, based on observational data analysis, to our knowledge about this causal cycle here. And I try to look at this now using the methods of causal discovery. So when you look at correlations between these three variables, everything is correlated with everything, lagged in each direction that you can think of, which is because the variables are highly persistent, they're very autocorrelated. If you now look at bivariate Granger causality, the one that worked before, then here it doesn't work. It still gives you a connection of everything with everything because it doesn't control for a third variable. So here, between the East and the West Pacific, it does not remove the effect of the Central Pacific, for example. And if you do so as a multivariate approach, and that PCMCI stands for, well, if I give you the acronym, it's kind of embarrassing, but it's like Peter and Clark are the first names of one of the two guys who invented an algorithm that this is based on, and MCI stands for momentary conditional independence. So this approach I developed over the past years, and this is adapted to time series and the challenges of these kind of data. And that helps you to find out that there is this causal cycle of East Pacific driving Central Pacific, driving West Pacific, and then you have a loop back that we know is through the higher troposphere. But of course, if you just look blindly at the data, you just don't know how this is mediated, but you just know that there is such a relation. So mediation is something that I think is quite important. And in this work of 2015 now, we looked at how El Nino drives Indian monsoon within the sea level pressure system. And that helped to identify here that this relationship, at least within the pressure system, is more mediated through the Indonesian archipelago here, while you also get a causal chain through China up there. But that chain is rather weak. So this mediation analysis is a framework that helps you to, given such a causal graph, to tell you, well, if there's more than one mediators of a causal effect, which one is more important and how? So that quantifies how much an intermediate variable contributes to a causal effect. And yeah, work on this is actually really, really early, even at the time of Sir Gilbert Walker, but in genetics by Cyril Wright, who was one of the pioneers of this. Maybe quicker here. So I mentioned before that I'm trying in my work to connect this causal discovery with, well, climate models that we have. And one first approach is to try to better evaluate which climate model better models the real data. And what we propose in a work with Per Novak here last year is you have real world data and you have model processes. And what people often do, of course, and what is, of course, the first thing to do is look at evaluations of, say, average variables. How well does a model represent the observed temperatures or so, and mean temperatures? But what if you, well, use a certain, define some variables based on your observed variables, and they may be, well, either averages over certain regions, but they really can be anything that you can come up with. Then you look at their causal network using one of those algorithms that I presented. And then you do the same in the space of modeled systems. Say you have 4 different models, and then you rather compare the causal graphs. And the intuition is, well, maybe that's a good complementary way to assess whether a climate model also represents the causal dependencies similar to the real data, rather than just means and maybe spectrums and, well, climatologies. So that's another way to look at it in this process-based model evaluation. theory or concept. So more on this in the paper. To summarize, I hope I gave you an intuition of causal inference as a way of answering causal questions from empirical data. I presented two settings, one of them being that you have your background knowledge and you know the graph qualitatively, but you do not know how strong the effects are, what the coefficients are in a linear way. And that first part was addressing this. Secondly, you didn't want to assume the graph, and that leads to causal discovery to get a graph or at least some information about the graph. And based on that, you can, of course, then do the same work as before on estimating causal effects. So both of these required assumptions. There's no free lunch. There's no just machine learning solving your problems. You will have to make assumptions like, well, we assume there is an underlying structural causal model, and we assume the causal Markov condition that separation in the graph leads to independence in the data. And the other direction, that if you measure an independence, then there is actually no connection between the two. That is an assumption that can be challenged. You may need to want to be willing to assume that there is no other relevant confounders. Maybe the graph that you draw or the variables that you have, you are safe that they represent all confounders in a certain system for a certain relationship. You can make assumptions about dependency types like linearity and the distributions. And time series data helps you because you have time order as a kind of an orienter of lagged links. On the other hand, you may have to assume stationarity, but there's work to overcome that partially. But stationarity is also an assumption that helps you. If you're not able to make it, you will get less knowledge about or you will get a less informative outcome. So these assumptions, they can sometimes be tested, like linearity or so, but often they can't. And therefore, your causal conclusions will require, when using such methods, will require you to state your assumptions and explain reasons for believing them, and maybe indicate how your conclusions would be altered. So maybe look for different hypotheses and test them. And with that, I would like to close, and there's plenty more references. So that's this perspective paper I mentioned. You can read the full book of Pearl, or you can read a primer that he wrote. You can read even a more simplified paper of Pearl on linear models, and maybe as a bedtime lecture, the popular science book that he wrote. And then there's more literature on other parts that you can look into here. And that's the software that Tom mentioned that also has a lot of tutorials to help you get started. Okay, that's it. Thanks.
Great, thank you, Jakob. So we'll take the next 15 minutes for questions for him. So remember, if you have a question, use the raise your hand button, or you can type it into the chat box. So with that, I see that Amy Braverman, you have your hand raised. Do you want to go ahead and unmute yourself?
Sure. That was a really nice talk. Thank you very much for that. I was at UCLA as a graduate student when Judea Pearl was coming up with some of this, and I have to admit, I'm a statistician, and I have kind of a initial visceral pushback on this that leaves me in a position that I hear a talk like yours, and I'm not sure whether this stuff is really good or really bad from the point of view of a statistician. I mean, obviously your work is very nice, but one thing that struck me was I don't see anything in here that actually requires going outside of the notion of statistical models. It seems like what's happening here is you, Judea, are being very bold and getting behind the simple kinds of assumptions that one ordinarily makes, and delving into how you would represent much more complicated kinds of conditional relationships. I mean, here on this slide, for example, where you say do x equals x, you're basically holding, you're holding x fixed at some constant value.
But
So
it's,
that is conditional.
but it's crucially not taking your observational data and looking for instances where your capital X is your lowercase x, but is the do quantity on the left-hand side is one that you cannot measure from data. It's the one where you intervene in the system, which is hypothetical. So that's the achievement, I would say, that he introduced this other mathematical object, which is this do calculus, in order to frame all his, well, the notion of causal effect in a mathematical way.
That's interesting. I'd like to hear more about that and think a little more about that. Perhaps I have a side conversation with you about that, because I still cling to conditional probability and to the relationships that it's capable of expressing. The other kind of broad question I had was, what's the relationship to structural equation modeling, which is also something that I think Peter Bentler at UCLA, as far as I know, is the one that developed that. There may have been someone before him. That seems similar in terms of variance relationships.
No, it is related. It's, well, maybe they came up with a new word because structural equation models often have been restricted to linear settings, and here they use this also because, of course, there's this relation with the do operation, and it should be non-parametric and more general in a certain sense. But I'm not the one to dispute all the little differences that people have come up with there, but it is quite related. So you're fine with thinking of it similarly.
Yeah. One last comment, which is that I'm at JPL, and we create a lot of observations or quote unquote observations from remote sensing. And there would be quite a number of issues here if you were using remote sensing data for any of this, because it is not direct observation, right? These things that you find when you go to the data center, and it's true of ESA data sets and everybody else who creates these things, these are all inferred from spectra. And there are uncertainties in those inferences, and they're all kind of embedded with the assumptions of the models that were used to retrieve the geophysical properties from those spectra. So it's not for the faint of heart, quite obviously, right? You have to be quite careful, I imagine.
Yeah, I mean, causal discovery inherits all the issues that you have also in usual data analysis when you have those measurement errors.
Yeah.
And they're difficult to overcome, of course. And it's, again, one topic where you need to make assumptions to overcome them. Like, as you said, use inverse modeling to retrieve the variable of interest from your remote sensing data, which comes with some issues. But there's actually also work on given measurement errors, under which assumptions can you still infer something, if not all variables are have measurement errors, and there's quite some work on this also. So
you can always throw up your hands and say, well, there's nothing I can do. And you can't do that, really. So anyway, I wanted to compliment you on the talk. It's very nice, very understandable.
Thanks.
Very interesting.
We have a question from Tom. Go ahead.
Thank you for a very pedagogical talk on causal discovery. It was really great. While we're on this slide, I had a question about the challenge number 3. Arguably, a lot of our dependencies in the climate system are nonlinear. So how did you, what tools did you and others develop in the causal discovery community to still apply this framework for relationships are nonlinear in the climate system?
I mean, the nice thing is that nowhere in the work actually usually you make, in the theory at least, assumptions about relations. So I mean, you know this, but for exposition, in the causal, like giving a causal graph, for example, when I have this general equation down here, you can fit that with your favorite deep learning or KNN or whatever machine learning tool, your regression tree, and you will get the correct result. It's about which variables to include in your machine learning model that causal inference helps you. And then you make another assumption on whether your relation is nonlinear, and then you should use a machine learning tool. While if you can make the assumption that it is linear, you should use a linear model, because generality always comes with a trade-off. That's the theorem of free lunch. So this function f here that you that exactly can be a deep learning model or so. And on the other hand, in causal discovery, going forward again, when I write this x1 independent x3 given x2, then that can be tested with partial correlation, which makes the linear assumption, or with conditional independence tests, more general ones. And I've developed one of them, and they do not assume linearity anymore. And they cover different types of nonlinearity, be it, say, nonlinear additive with additive noise or other types. So that's a big field, and there's in Tigermite, in my software package, there's quite a number of those tests already to help you with this. But they take time to compute.
Yeah, that was exactly going to be my follow-up question. What is the trade-off when you use a conditional dependency test that's adapted for nonlinear relationship? Like, is it 10 times as long, or?
Well, it super depends, but 10 times is a lower bound maybe, because it's something big that you want. You want to not make a linear functional dependency. I mean, what you can do is maybe your polynomials that it relates to, then you pre-process your data basically, then it's fast. But if you want to go for Gaussian process regression as a general tool, then you end up with time complexity of, I don't know, squared or whatever, and then you are up in the hundreds of complexity. But you can overcome this with all kinds of technical tricks on GPUs and so on. And we also have some of that implemented in Tigermite, GPU parallelization and so on.
Yeah, thank you. That perfectly answers my question.
I see a question in the chat box by Noah Brunowitz. And Noah, feel free to unmute yourself if you want to elaborate more. He asks, are there any fields where causal inference is a moderately agreed upon modus operandi for scientific discovery? Do these have similar data to geosciences?
Good question. So there's fields where, like in genetics, where people are able to make experiments, but they are expensive, and they would use causal discovery to pre-filter where to look for relationships. Say you find that there's no link in your observational causal graph, then you do not need, under some weaker assumptions, you do not need to look for, you do not need to conduct these experiments. While if you find links, but you made the assumption of causal sufficiency, then you would still need to test that link, maybe in an experimental setting. So there, in medicine also, it's about life and death. So the modus operandi would be to do such things before, to come up with maybe good recipes for treatments. And in many other fields, this is being used because experiments are expensive in many fields. Like, I don't know, in industry, what Google does or so is, a lot of that is also causal inference to test what ad campaigns or whatever would work in principle. And then they partially can test that too, of course, being Google. Moderately agreed upon modus operandi. Yeah, that's maybe what I can say about that. It is all based on how well you present the assumptions that you do, and then you can argue about them. It is certainly a step forward from just using correlation and regression analysis.
Okay, yeah, thanks for asking the question. Yeah, I mean, it seems like something that's like with genetics, at least that, like, the genes come first. Same thing with the time ordering. So it seems like there's some kind of directionality to potential causal graphs there that's enforcing some kind of sparseness on like the available relationships between observed quantities. I guess I could can see there's some similarity there.
Yeah.
But
Yeah, I'm just reading here, popular, of course, in social sciences also, yeah. But the data is often different. I mean, we have dynamical system underlying here in social sciences. The data is us, like individuals, and you have other problems there that you don't have in climate so much. But certainly social sciences like economics or policy interventions, econometrics, they are in the group that opposes the language of causal inference for a long time. And if you're on Twitter and look for Pearl, then you can see his Twitter wars with the econometricians and economists. They seem to be a little more conservative in adopting other things.
oh, I won't jump in. There's another question, but I had a follow-up, which I can ask later.
Yeah, I'm reading Carl Friston in neuroscience. That is, it is also similar. You in that framework also assume certain graphs and then use a dynamical model to estimate relationships, but it's a little bit of a parallel world, and it can be framed in this framework.
I had a follow-up just in terms of like when I write down a PDE on a piece of paper and then, implement that and make a simulation with it. I mean, isn't really the thing causing that me writing down the PDE? And so is there any notion of kind of like extending this ABC from like scalars or Boolean variables to like functions or operator spaces like that that are causing changes on observables?
So in general, this ABC stuff is not restricted to univariate variables. That can be vectors. But I mean, trying to connect PDEs. I mean, what basically makes up a climate model to these nodes here is this difference between the microscopic level at which you have the PDEs working, and then being emulators of the underlying physics. They give rise to macroscopic behavior, and it's not intuitively clear giving a PDE whether even if you have your climate model, you cannot say whether Enzo causes another region if you don't do the experiment with your climate model. But I mean, the PDEs underlying the climate system you are just connected to your neighbor grid box. Of course, that's the stencil of a PDE, but the macroscopic relations that emerge from this are what I would here consider as the question of interest. There's some people looking into, for example, connecting ODEs to structural causal models, because an ODE, of course, also captures a time dependency structure, and that is something in that direction. There's physicist Joris Moi working on that. It's an interesting relation, but most of Perl or so, they don't think so much in PDEs, so they develop this in another state of mind.
Great. So I have 4 o'clock Eastern time right on on my side. So I think with that, we'll end today's webinar. So thank you so much, Jakob, for giving us the talk today.